Every single day, you're navigating this hidden world, a massive invisible network that, well, it quietly runs your entire digital life. So today, we're going to hand you the map that makes it all work. I mean, seriously, think about it. How does Google Maps find the absolute fastest route in like a split second? Or how does Netflix just know what you want to watch next? It feels like magic, right? But it's not. It's actually something way more structured and, honestly, pretty elegant. So what's the secret? Well, it's not a road map. It's more like a subway map for data. This is a really powerful idea from computer science called a graph. And yeah, you can forget about the x and y axes from math class. For our purposes, a graph is just a map of connections, a huge subway system where data zips from station to station. All right, so to really get how this thing powers, well, everything, we first have to learn how to read the map, even how to build it. And don't worry, it all starts with just two super simple components. First up, we've got the vertex, or vertices if you're talking about more than one. Think of it as a single station on our subway map. It's the destination, the point of interest. But here's the cool part. In the digital world, a vertex can be pretty much anything. It could be you on Facebook, a product on Amazon, or, a city on a real map. Okay, so you've got stations. But what good is a station without a track connecting it to another one, right? That's where the edge comes in. The edge is just the track connecting two stations, two vertices. It's the relationship, the path, the thing that turns a bunch of lonely dots into a really powerful network. Now it gets interesting because not all tracks are created equal. You have what are called undirected graphs. The easiest way to think about this is a Facebook friendship. If we're friends, the connection goes both ways. It's a two-way track. But then you have directed graphs. These are one-way streets. Think about following a celebrity on Twitter. You follow them, but that doesn't automatically mean they follow you back. The connection only goes one way. And this next part is where our map gets really smart. See, an unweighted graph just says, yep, a connection exists. That's it. But a weighted graph, that tells you the cost of that connection. For our subway, that weight could be the travel time, right? Or maybe the price of the ticket. This is so important because it's how an app knows that a route with 5 stops might actually be way faster than a route with only 2. Okay, so we've got our map, we have our stations, our tracks, but there's a problem. A computer can't see a drawing. We need a way to translate this whole thing into a digital language that a machine can actually understand. And there are basically 2 main ways to do this. First, you have something called an adjacency matrix. Imagine a massive grid, like a spreadsheet, with every single station listed across the top and down the side. You just put a check mark where 2 stations connect. It's super fast to check a connection, but man, it uses a ton of memory for all that empty space. The other way, which is often more popular, is the adjacency list. This is more like a contact list for each station. Every station just keeps a little list of the other stations it's directly connected to. It's way more space efficient, but might be a tad slower if you need to look up one specific connection. All right, our map is built, it's digitized. Now for the fun part. How do we actually use it to get from point A to point B? To do that, we need a navigation plan, a set of rules. In computer science, we call these algorithms. Our first strategy is called breadth first search, or just BFS. Imagine you're standing at a station. BFS is super methodical. It explores layer by layer. So first, it looks at all the stations that are just 1 stop away. Then it looks at all the stations 2 stops away, then 3, and so on. Its goal is simple but really powerful. It always finds the path with the fewest number of stops. Guaranteed. The other main strategy is completely different. It's called depth first search, or DFS. Think of this one as the adventurous explorer. Instead of going layer by layer, DFS picks a path and just goes. It goes as far down that one track as it possibly can. When it hits a dead end, it just backtracks to the last choice it made and tries a new path. This is great for things like solving a maze or if you just need to visit every single station without caring about the order. Okay, but here's the million-dollar question. BFS is great for finding the path with the fewest stops. But what about our weighted map, the one with travel times? A 2-stop trip could take forever if the train is slow, while a 5-stop trip on an express line could be super quick. So how do we find the path that's actually the fastest? To solve that, we need to bring in the big guns. We need a smart GPS. And in the world of computer science, that smart GPS has a name, Dijkstra's algorithm. This is the absolute genius behind things like Google Maps. And the core idea behind it is actually brilliantly simple. Dijkstra's is what we call greedy. All that means is, at every single station, it looks at all the possible next stops and always chooses the cheapest one, the fastest one, the one with the lowest cost. What's so amazing about it is that it's smart enough to find the best overall route without having to check every single possible combination, which on a big map would be literally impossible. It's just constantly finding shortcuts and updating its plan as it goes. Okay, so let's recap. We've built the map, we've turned it into data, and we've figured out how to navigate it. So now, for the big reveal. This isn't just some abstract computer science theory. This subway system, it's running right now, all around you. Think about your social life. How does Facebook find your mutual friends? It's just looking for people, vertices, that both you and someone else have a connection, an edge, to. Simple. And Twitter? The whole thing is just one gigantic directed graph, a massive one-way subway system of information and influence.
And it gets bigger. The entire World Wide Web is a graph. Every single website is a station, and every hyperlink is a one-way track to another station. You know Google's famous PageRank algorithm, the thing that decides what comes up first in a search? It's basically a massive graph problem, trying to figure out which stations are the most important by seeing how many tracks lead to them.
And finally, let's talk about your entertainment. How does Netflix do it? Well, you're a station. A movie is another station. When you watch and rate that movie, you're creating a weighted track between the two of you. The recommendation engine just looks for other people who have a subway map that looks a lot like yours, and then suggests the stations you haven't visited yet. It's that simple.
So, you see, when you strip it all away, graphs aren't just a boring data structure. They are the mathematical language of connection. They're the blueprint for how everything is connected, from people to websites to ideas. This is the invisible architecture behind social networks, GPS, even mapping the human genome. Understanding this stuff, it's like someone just handed you a secret map to the entire digital universe. And the best part is, now you know how to read it. So the only question left is, what are you going to build with it? Thanks for watching. See you tomorrow.